Good morning, good afternoon, good evening. We are back and better than ever. We are talking about lines in two dimensions. And we're talking about that dealing with vectors, of course. Um, in both two-dimensional and three-dimensional geometry, we can find the equation of a line using its direction. You can think of that as slope and any fixed point on the line. If you think of point slope, if we had a point and we found the slope of a line, we were able to find its equation. The same is true with vectors. It's just the way we talk about it is a little bit different, and the way we think about it is a little bit different. So I'm going to go through all this and don't fade off because this is really important. So they're giving us an example here. Suppose a line passes through a fixed point A. So this point right here, point A, with position vector A. So the position vector, remember, emanates from the origin. So this is the origin, and to get to point A, we go so many units to the right and then so many units up. Remember, that's what position vector means. Okay, and that the line is parallel to the vector B. So this is the line they're talking about right here, and they're saying that it's parallel to this vector B. Okay. So then they say consider a point R on the line. So this point R could be anywhere, but they're saying it's here, any point R on the line, and they are saying that vector OR is equal to the little vector r, and they use the little vector r as the resultant vector. So OR, and this is what they're saying right here, vector OR from here to here is equal to vector OA plus vector AR. In fact, I'll draw that in there for you. You know, if we draw this vector in here, you can see that's how we add vectors geometrically. Okay? All right. So it comes down to that the vector equation of a line is given by r is equal to some vector a plus ar. And since vector AR right here from here to here is parallel to B, and we know that because this line is parallel to B, then vector AR is equal to some multiple of B. In this case, it might be, looks like vector AR might be twice the size of vector B. So maybe this T is a 2. We've talked about that before. And because of that, the vector equation of a line is given by this right here. R equals A plus T times B. Now R stands for any point on the line. Okay, this is the vector equation of a line. A is a known point on the line, and right here that represents this point right here. And then vector B is the directional vector of the line. You can think of that as the slope. And then T allows it to, is the parameter, and we'll talk about the parameter in just a second. Okay, so if you didn't quite follow that, I think you will by the end of the video if you pay attention. This is the only help we get on our formula sheet. The vector equation of a line is r equals a plus tb. So we have to remember that that r is any point. Any point. Okay? And a is a fixed point or a known point on the line. And b right there is the direction vector. Which way is this line going? Okay? You can sort of think of it as slope. You'll see what I mean in a minute. Okay, so in two dimensions, obviously we are dealing with a line in a plane. Okay? Not in space, a line in a plane. Okay? Now, remember back before, this is still the vector equation of a line. This is the vector r. This is little a, vector a, right? And this is little vector b, the directional vector. The xy, maybe it's a bit more clear to you. Xy represents any point on the line. Any point on the line is going to have an x coordinate and a y coordinate. But in vector, making it simpler, we'll just use r because it was the resultant vector back here. This vector right here, little r. It came from adding these two vectors. So any point on the line, xy, is given by a known point plus some multiple t of the direction that the vector is going. Okay? And here they use cap r and cap a just because that's how they labeled it here. R, cap a, and then here's the directional vector b. Okay, for this line that they're telling us right here. Okay. Now, the gradient of the line is m equals b2 over b1. What's that all about? Well, remember, this is vector b. Think about this. This is, I keep doing that. This is b1, b2, right? Those are the components of the directional vector b, right there. The directional vector. What direction is the vector going? Well, remember that the components of a vector, the top one is the horizontal direction, which we know very well as the x direction, and this is the vertical direction of the vector. Vertical, which we know very well as y. And we know that slope is equal to change, delta is change, delta y over delta x. That's all this is. The slope is the change in y over the change in x. The change in the vertical compared to the change in the horizontal. Okay, so that's where that comes from. Okay, so all this is a rewrite of this equation right here. We can write what are called parametric equations of the line, and all we have to do is say, okay, my x is going to be equal to the component a1 plus the component b1 times the parameter t. The parameter, it's like a multiple, and this is why it's called parametric equations, because of this parameter. Sounds really complicated, but it's not. We can get our x coordinate using this, a1 plus b1t, and our y coordinate equal to a2 plus b2t right here. And each point on the line corresponds to exactly one value of t. That becomes important in a second. Okay. Then we can convert each of these equations into Cartesian form. This looks really confusing, but it's not. It's really not. Take a look at this equation right here. If I solve this equation for t, I get that right there. If I solve this equation for t, now this t is the exact same thing as this t, I get that. So t equals x minus a1 over b1 equals y minus a2 over b2. They're all equal. This is mega confusing, and you'll see in the example how it doesn't have to be this hard. But all this really is the standard form of a line ax plus by equals c. Because all of this right here are just numbers, and x and y are variables here, and a and b are the coefficients. All right, so let's put this into use. Okay, or let's see what we have to do, how we're going to use all this information. A line passes through the point A, 1, 5, and has direction vector 3, 2. So right away, I know this is my little a, okay, and my direction, this is my little b, okay, and I cut these and pasted them here as our little guide. This is the vector equation of a line. This is my r, this is a plus some vector b times parameter t, or tb. Okay, either way. So how do we do that? Well, x, all we need is a and b, some fixed point on the line. Well, a, all I need is the position of it. It's a positional vector, And if I think of vector OA, where O is the origin, that gives me 1, 5. Because what are the coordinates of the origin? 0, 0. 1 minus 0 is 1. 5 minus 0 is 5. So xy is very simply going to be equal to a1, a2, or 1, 5, plus t times the directional vector, which is given 3, 2. And there we have the vector equation of the line. Again, this is R. Any point on the line, this is a point that we know for sure, and this is the directional vector B, right here. Okay, part B, what are the parametric equations? Very simple, okay? If xy equals a1 plus b1t, which is what we have right here, then the parametric equations come right from our vector equation. The parametric equations are x equals 1 plus 3t, which I got going just straight across here, multiplying t by 3, and y equals 5 plus 2t. Easy peasy pumpkin pie. All done. Okay. What about a Cartesian equation? These are the equations we're used to with just x's and y's. What they're saying is, all right, go back to the geometry that we understand. Well, to do that, we just have to solve each of these for t. So I'm going to solve this first parametric equation for t, and that would give me t equals x minus 1 over 3. And if I solve this for t, it would give me, let's see, t equals y minus 5 over 2. Well, these t's are equal, so therefore, I'm going to have to work over here now. X minus 1 over 3 must be equal to y minus 5 over 2. Now, I need to get it in some recognizable form, like slope-intercept or standard form. Remember I said standard form is ax plus by equals c. That's going to be the easiest one to do just by cross multiplication. If I cross multiply, I get 2x minus 2 equals 3y minus 15. And then I get my x's and y's on the same side. Moving 2x over here, I get 3y minus 2x. If I add 15 to both sides, plus 15 here, plus 15 here, I end up with 13. And there is my parametric equation. And there you go. See you next time.